under 1 million qubits. That's Google's newest estimate for how many it takes to break the encryption guarding your bank account, your messages, your medical records, in under a week. 6 years ago, that estimate was 20 million qubits. It has dropped 20-fold. So how close is this thing really? In this video, what a quantum computer actually is, in plain English. Where Google, IBM, Microsoft, IonQ and China's labs really stand in mid-2026. The encryption threat that has already started. And the reality check, what these machines still can't do. No hype, no doom, just the honest picture. First, the basics. No physics degree required. Your laptop thinks in bits. Tiny switches that are always either 0 or 1. A quantum computer uses qubits. While a qubit is computing, it's like a coin spinning in the air. Not heads, not tails, but a blend of both at once. Here's why that matters. Link qubits together. Physicists call it entanglement, and every extra qubit doubles the number of possibilities the machine can juggle simultaneously. Double, double, double. By 300 qubits, you're juggling more states than there are atoms in the observable universe. That's the raw promise. But here's the catch nobody puts in the press release. Qubits are absurdly fragile. A stray vibration, a whiff of heat, even a cosmic ray, and the calculation collapses into noise. Today's physical qubits make an error roughly once per 1,000 operations. Useful algorithms need billions of operations in a row. The fix is error correction. Bundle hundreds of flaky physical qubits into one reliable, logical qubit that catches its own mistakes. That is the whole game now. When you hear logical qubits, that's the number that matters. And it's why raw qubit counts in headlines are mostly marketing. So where is everyone in mid-2026? Start with Google. Its Willow chip did something genuinely historic. For the first time, adding more qubits made errors go down instead of up. That's called going below threshold. Proof that error correction really scales. Physicists chased that milestone for almost 30 years. Willow also ran a benchmark in about 5 minutes that Google says would take today's fastest supercomputer 10 septillion years, a 1 with 25 zeros. Jaw-dropping? Yes, but be careful. That benchmark is a contrived test designed to favor quantum machines. It computes nothing useful. Keep that distinction handy. IBM is playing a different game, engineering over fireworks. Its 120-qubit Nighthawk chip is chasing verified quantum advantage, a speed-up independent researchers can confirm by the end of 2026. This June, IBM committed more than $10 billion to its roadmap. The destination, Starling, a fault-tolerant machine, in 2029. IBM's secret weapon is a smarter error correction code called QLDPC. It cuts the physical qubits needed per logical qubit by roughly 90%. If Starling lands on schedule, it will run 100 million operations on 200 logical qubits. That's the class of machine chemists are actually waiting for. Microsoft is the wild card. It spent nearly 20 years betting on exotic topological qubits, which are supposed to be stable by design. Its Majorana chips have drawn real scientific fire. Some physicists questioned whether the first one even worked. This year, Microsoft reported a 1,000-fold stability improvement. Promising and proven, worth watching. Then there's IonQ, which computes with individual charged atoms held in electromagnetic traps. Fewer qubits, but some of the highest accuracy in the industry. Its roadmap is aggressive. Around 20,000 physical qubits by 2028, 2 million by 2030. Ambitious. And remember, roadmaps are promises, not products. And China? Very much in the race. The Zhuangzi 3 chip from USDC posted a sampling benchmark 10 to the 15th times faster than a top supercomputer, rivaling Google's class. Its machines already run on a public quantum cloud serving users in over 60 countries. This is not a one-country race. Now the part that affects you directly, encryption. Almost everything private online, your banking, your chats, your saved passwords, leans on math problems that classical computers cannot crack in any reasonable time. Back in 1994, mathematician Peter Shor proved that a big enough quantum computer solves them almost casually. How big is big enough? Google researcher Craig Gidney ran the numbers in 2025. Under 1 million physical qubits could crack a standard RSA key in under a week. Today's biggest chips hold around 1,000. That's roughly a 1,000-fold gap. Big, but shrinking faster than almost anyone predicted. Here's why experts aren't relaxed about that gap. It's an attack called harvest-now-decrypt-later. Intelligence agencies and criminals are recording encrypted traffic today, yours included, to unlock the moment hardware catches up. Medical records, state secrets, contracts, anything that must stay private for decades is already exposed. The defense already exists. In 2024, the U.S. standards body NIST finalized post-quantum encryption, new math that even quantum computers can unpick. Washington has since ordered critical federal systems to switch by the end of 2030. Cloudflare, Google, Apple, and Signal have quietly upgraded traffic for billions of users. But here's the ugly number. As of this year, only around 13% of enterprises have actually deployed post-quantum encryption. The rest are gambling that Q-Day arrives late. The real threat isn't a quantum computer appearing overnight. It's slow migration colliding with stolen data that's already sitting in storage. Time for the reality check, because this is where hype goes to die. Ask one brutal question. Has any quantum computer solved a real problem? One somebody would pay for? Faster than a regular computer? In mid-2026, by any widely accepted measure, the honest answer is still no. Not yet. The record-breaking demos are custom benchmarks with no practical output. The largest numbers genuinely factored with Shor's algorithm remain laughably small, the kind you could do on paper. And no, quantum won't speed up your games, your spreadsheets, or your chatbot. It's a specialist instrument, not a faster laptop. What it should eventually be brilliant at: simulating nature itself. Drug molecules, battery chemistry, fertilizer catalysts, new materials, problems where classical computers choke because nature runs on quantum physics. That's why chemists and pharma companies are watching those 200 logical qubits like hawks. Nature speaks quantum natively. So when surveyed experts now cluster around this narrow, provable advantage on specialized problems within 3 to 7 years. Broad commercial usefulness, more like 7 to 15. Breaking real encryption. Most estimates say the early to mid-2030s, if the roadmaps hold. Notice what quietly vanished from serious forecasts: the word never. My take: 2026 is the year quantum computing stopped being a physics story and became an engineering one. Below-threshold error correction was the checkpoint everything else depended on, and it's done. What remains is a grind: better qubits, smarter codes, factory-scale manufacturing. Grinds are boring. Grinds also tend to finish. Practical advice: ignore both extremes. Anyone selling you quantum stock tips because it changes everything next year is guessing. Anyone calling the whole field a scam is ignoring peer-reviewed physics. If you run a business, ask one question this quarter: where is our encryption inventory? That migration takes years. Start now. So, how close is quantum computing, really? Closer than the skeptics thought, further than the salesmen claim. The machines are real, the milestones are real, and the encryption clock is genuinely ticking. But the world-changing part is still a decade of hard engineering away, which, in tech time, is basically tomorrow. Here's my question for you. If a quantum computer could crack encrypted data harvested 10 years ago, what would you least want resurfacing? Tell me in the comments. And if you want technology explained straight, no hype, no doom, subscribe and hit the bell. See you in the next one.